You know, in just about any complex system, we're always making a trade. We accept some hidden cost in exchange for efficiency we can see. But what if that cost is total collapse? And what if it's a trade you never even realized you were making?
And the logic, it seems so simple, right? It's totally sound. In any system, a server farm, a traffic grid, a production line, one part can become a bottleneck, and it just grinds the whole system to a halt. So the goal is obvious. You've got to protect that one part from getting swamped.
But here's the twist. That totally rational act of protection, it creates this deep structural paradox. The very thing you do to stop one small part from failing, well, that's what sets the stage for the entire system to fail, catastrophically.
So take a look at this. On the surface, this system looks perfect. I mean, it's the picture of health. Every single part is just humming along at a nice, comfortable 70% capacity. The work is spread out perfectly, no red lights, no alarms, nothing. If you just look at the individual parts, you think, wow, this is a model of stability.
And then it just stops. No warning. Not just one part failing, all of them, all at once. A sudden, total, system-wide collapse. That perfectly balanced system, it's now perfectly dead. So, how on earth does that happen?
To get to the bottom of this, we have to stop looking at the parts and start looking at the structure. This is what we call the efficiency paradox.
Okay, so it all starts with a problem that's super obvious, right? Demand is never perfectly even. So you get one server, or one highway lane, or one person on a team who just gets slammed. Meanwhile, the rest of the system is just sitting there totally idle. All that capacity just wasted. It's inefficient. And of course, a problem like that demands a solution.
Let's think about this with a simple physical analogy. Imagine the work coming into the system is like water being poured into a set of beakers. In this unbalanced state, all the water is just pouring into that one beaker. And yeah, it overflows pretty fast. Meanwhile, the others, they're almost empty. The failures is local, it's visible, and it happens right away.
So what's the logical fix? Well, you install a load balancer. It's basically just a mechanism that takes all that incoming work and spreads it out evenly across everything that's available. The whole point is to make things faster and, crucially, to stop any one part from getting overloaded.
Now let's go back to our beakers. To fix our overflow problem, we connect them all with little pipes near the top. So now, when you pour water into the system, it just levels out automatically across all of them. No single beaker can overflow by itself anymore. It looks like we've completely engineered that bottleneck out of existence.
And on paper, this looks like a huge success. I mean, check this out. Before, you had server A just getting hammered at 100% capacity, while server B was chilling at 20%. But after you balance the load, they're both stable at 60%. The system feels more efficient, it seems more resilient, more stable, or so you'd think.
So what this solution gives us is a system that looks, well, perfectly balanced.
And I really want to stress this. This isn't just about computers. Not at all. This is a fundamental pattern, a deep structural thing that shows up in pretty much any system that's designed to be highly efficient.
Think about a city's traffic grid. It'll reroute cars to avoid one jammed street, and suddenly you've got gridlock across the entire city. Or a power grid that shifts load away from one generator that's working too hard, and in doing so, it risks a blackout for the whole region. Every time, it's the same story. A solution for a local problem creates a massive global vulnerability.
Okay, so here's where it gets really interesting. This balancing act, it creates this weird disconnect. If you ask any single part of the system how it's doing, it reports back, I'm fine. The local workload seems totally manageable. But what's hidden from view is that the total stress on the entire system is going up and up and up. And those local checks, they can't see it at all.
And that brings us to this really key idea. Let's call it global utilization. This isn't about the work on any one part. It's the total amount of work being handled by the entire system, all parts combined. And that is the number that is silently, invisibly, creeping towards a breaking point.
And this invisibility, well, it has a cost, a hidden one. A cost the system is literally designed to ignore.
Let's go back to our beakers, because here the consequence is crystal clear. As we keep pouring more and more water in, the level in every single beaker rises together. They're all linked now. Their fates are tied, and that water level is getting dangerously high everywhere, all at the same time.
So imagine the system's global utilization hits 99%. Every single piece is busy. But again, if you could ask one of those servers, it would just say, yep, I'm busy. There's no alarm for being almost overwhelmed. The system looks perfectly stable, right up until the second it's not.
Which, of course, leads to the big question. When a new request comes in and everything is already busy, where does it go? Well, it goes into a hidden waiting line. This isn't a queue for just one server. It's what we could call an implicit queue for the entire system. And that is the invisible price of balancing. The line gets longer for everyone, everywhere, all at once.
And this is what leads to the final state: simultaneous saturation.
The logic here is just inescapable. Let's walk through it. 1. We spread the work around to protect the individual parts. 2. By doing that, we tie the fate of all those parts together. 3. The total load on the system climbs, but it's hidden, masked by how efficient each part looks. And 4. Every single part hits its absolute limit at the exact same time.
We've now reached the point of inevitability.
And this is probably the most unsettling part of it all. The system's collapse, it wasn't a failure. It was the perfect execution of its own design. Think about it. The whole system was built to do one thing: distribute the load until no single part had any room left. And that is exactly what it did.
So that sudden total failure wasn't a bug in the system. It was the final logical outcome of the system's obsession with efficiency. The very thing we built it to do, when taken all the way to its conclusion, guaranteed its own destruction.